We would like to present the Technoton Glasstop Simulator. Each unit uses 3 touchscreen LCD monitors mounted to replicate the experience of a typical control room. This interactive tool is known as a Glasstop Simulator. It is possible to represent a complete control room using only one Glasstop. However, it is also possible to use units together as one simulator, as seen here with 3 units being used. The final objective is the simulation of the control room, but replacing the hardware panels with software equivalents. This has a number of advantages. At less than 1% of a normal full-scope simulator, the cost of a Glasstop is considerably less than a standard unit. It is far more realistic than a standard graphical interface simulator. Changes in the instruments are also easily performed. Furthermore, the unit is portable. The structure is smaller and is mounted on wheels, which allow easy movement from one location to another. The precision of the Glasstop is exactly the same as a full-scope simulator, since both use the same simulation. The only change is how the data is presented and manipulated. The other difference is that the full-scope simulator is usually only accessible to a licensed operator, whereas the Glasstop is accessible to everyone. In addition to the representation of the panels, the Glasstop has a menu in the lower right to select available options. The navigation between the panels is the same as a standard touchscreen device. In addition, we have an option to use a mini-map or a control room scheme. Once we have the screen focused on a particular panel, valves and controllers can be operated. We can select lights or lamps. It is also possible to use the zoom option to magnify sections of the panels. In terms of alarm representation, we have 2 options. Firstly, the alarm can be opened in the Glasstop. Simply select the alarm and the details and relevant links will appear on the screen. Secondly, the alarm can be displayed on an external device, such as a tablet. This option is selected as shown.
As an initial condition, the plant is at full power, when a condensate problem leads to all feedwater pumps concurrently tripping and causing an automatic turbine trip. In this situation, heat removal is severely reduced, while the reactor is at power. As a result, temperature and pressure in the primary circuit are increasing immediately. Right now, we can see how the pressure is increasing. Automatic pressure control actuates and spray valves open to try to maintain pressure. However, pressurizer relief valve set point is reached and valve opens to protect the integrity of the primary. When valve opens, pressure increases at a slower rate until reactor automatically trip. Protection system actuates to automatically shut down the reactor. After the trip, pressure and temperature decrease rapidly, but pressurizer relief valve fails to reclose. Now we can see how temperatures have dropped after the trip, and temperature difference in the steam generators is 8 Kelvin. After the reactor trips, primary parameters should stabilize at the normal no-load values. However, relief valve remains open when pressure lowers below the set point. That is causing a continuous drop in the primary pressure. Normal pressure is about 15.4 megapascals, but pressure at this moment is 7.7 megapascals and lowering. At the same time, steam generators are going dry as a consequence of a complete loss of feedwater. Auxiliary feedwater failed to actuate after the main feedwater pumps tripped, and steam generators can no longer be considered as a valid heatsink. Changing to a void fraction representation of the steam generator, subcooled water is represented in blue, and steam is represented in red. We can clearly notice the amount of subcooled water in the steam generators. Let's have a look at the void fraction of the primary. Right now, primary system is completely filled with subcooled water. However, temperature is increasing due to the low level in the steam generators, and the pressure is dropping rapidly as pressurizer relief valve has failed open. Steam will be formed very soon. First part of the vessel to boil will be the upper parts. Void fraction in the reactor vessel head increases, and these bubbles are pushing water to the pressurizer, where a sudden level increase occurs. We see clearly how the pressurizer is almost completely full, while the reactor vessel head is bubbling. More and more water is converted into steam. A mixture of water and steam circulates through steam generators, and the heat transfer lowers. Going back to the void fraction view, we see that the bubble in the reactor vessel head is expanding, and primary coolant in the hot legs are no longer in subcooled conditions. Steam bubbles are pumped through the primary circuit. Reactor coolant pumps are not designed to pump steam, and they start cavitating. Pumps are manually stopped at this point for pump protection purposes. Circulation of bubbly water through the core stops, and the core cooling is severely affected. Let's go back to the void fraction. As the bubble in the reactor vessel head expands, the core will uncover very soon, At this moment, core is at saturation conditions, but with the core temperatures rising, superheated steam will be created in the upper parts of the vessel. With the core being cooled by superheated steam, fuel elements will finally fail and core geometry will be severely affected. Before that happens, core injection is established through the three cold legs. Cold leg temperature at this moment is lowering after the core injection. As time goes by, this cold water injection will collapse the reactor vessel bubble. After several hours of simulation, this is the aspect of the primary circuit. Bubble in the vessel has collapsed and the primary circuit is completely full of subcooled water. Core is cooled in a feed and bleed circuit. Cold water is being injected into the core while water is discharged through the still-failed pressurizer relief valve.
The simulation process is one of the pillars of the 4.0 industry. It consists of performing virtual models that reproduce the related variables in the power plants and real installations. Through the simulation, digital twins can be developed in order to analyze the multitude of data and improve the decisions that have to be taken or the knowledge of the subject. To simulate these complicated processes and support the operation of industrial facilities in an easy and intuitive way, Technotom has developed a set of tools and simulation codes called TeamSuite Technotom Advanced Modeling Tools. TeamStation allows the interaction with the simulation so that failures can be introduced, such as breaks in pipes, short circuits, or failures in control logic. It also allows analysis of the behavior of our system before these events happen in reality. TeamTutor is used for the management of scenarios and self-study exercises, and to program by default various events to be reproduced later. TeamSketch faithfully simulates the interaction environments with the real installation. This is the human-machine interface, the controls, displays, and operation panels. In addition, new interfaces can be designed based on the philosophy of high-performance displays to provide the monitoring and operation of critical system parameters. Team Electric simulates all electrical systems in a realistic way, both of electrical installations of power generation plants and electrical grids. It analyzes and executes the different behaviors of the grid in real time: power flows, voltages, frequencies, and transients. TeamFlow is used for the resolution of hydraulic systems, liquids and gases. It calculates the pressures and temperatures of the fluid, as well as the mass flow in the elements of a hydraulic circuit. Likewise, the transport of substances and the heat transmission are calculated. TeamLogic executes the control and protection logic. It has a library of icons adapted to the needs. It's a powerful program that serves for the assimilation of control logics and for the validation of new changes in the installation. TeamSuite allows the creation of models from graphic sheets and the generation of their associated code, the integration of the code in a simulation environment, including the management of the database, the connection, visualization, and modification of variables in real time, the real-time and synchronized execution of the different modules both from the Team Suite environment and from third parties. The debugging and adjustment of the models with Microsoft Excel as the developer interface and the document control environment. In addition, Technotom has developed automatic translators of distributed control systems and its operation interface. These tools are compatible and integrable with each other, achieving a single graphic environment which is easy to implement. The international success of Team Suite is supported by its use in more than 60 power plants and electrical grids.